theory of local times and self-intersection local times. Exactly what I plan to discuss today is some representation, okay, for the local time and for the self-intersection local time. Of course, what we did before is that we proved the existence either by the density of the occupation measure or as a limit of approximation. And that's all. But today we'll present some explicit expression, some representation of this local time of the self-intersection. And in the second part, there are two parts. In the second part, I will talk a little bit about polymers and what is the link between self-intersection local time and polymers. Why is this theory is important in other fields rather than mathematics? So I recall first the useful result that I presented yesterday. So first of all, the definition of a Gaussian integrator. Maybe the first definition is also a little bit complicated. So we use always this representation of Gaussian integrator, which is more efficient and practical. Okay? So a Gaussian integrator is given always by this integral. There is an operator in L201, a bounded linear operator, and we integrate. We compute the action of this operator on the function indicator of 0t. We compute this function and we integrate this with respect to the Brownian motion. This is called the Wiener integral, since this function integrated here is deterministic. So this integral is not such complicated. And under the condition of invertible operator A, this stochastic process here has a local time given, for example, by this L2 limit of this family of random variables. Okay. Here, I will present a Clark formula for this local time. Okay, for this local time. But first, I will begin by the Brownian motion, okay, for the local time Brownian motion, and then I will present another formula, a similar formula, but for general Gaussian integrators. I recall that the Brownian motion is, yes, I'm coming back. I recall that the Brownian motion is the first example of Gaussian integrators. Okay? So this is a class of stochastic processes that contains the Brownian motion, the Brownian bridge, half of the family of the fractional Brownian motion, and many others well-known Gaussian stochastic processes. Okay, we start by the Brownian motion. So, first of all, what I mean by Clark formula is the following. Okay, so that is a Clark formula. So if we have a random variable, alpha, okay, random variable, which is a random variable, I will just write random variable, which is square integrable, okay, L2 omega. When I say L2 for random variables, it means that L2 omega, we put here the space, the probability space that we use, okay, even if I don't recall it. So it is square integrable as a finite second moment, and we suppose that it is measurable with respect to the Brownian motion. The sigma field generated by the Brownian motion. Mainly, it is a function of the Brownian motion. It depends only on the Brownian motion. For example, maybe bt1 to the some power or some function of bt1, bt2, btn. Okay? Anything that only depends on the Brownian motion. And it is square integrated. This kind of random variable can be written in the following form. The expectation of alpha plus a stochastic integral here, 0 to 1, of something, let's say, x of t, t, dt. This is the Clark formula. This kind of formula. Okay. I write the random variable as its expectation plus the stochastic integral. Okay? We call this kind of formula Clark formula.
Do you have any restriction to xt? So the integral exists. Stochastic integral.
Of course, xt will be square integrable and adapted so that this integral is well defined. Okay? Okay. So what I want to say here, if the random variable can be written in this way, we call this a Clark formula. Okay? Of course, it exists for all such kind of random variables. Okay? And in some specific cases, we even can have an explicit formula for this XFT. It can be obtained from the stochastic derivative of alpha and so on. I will not go into these details. This kind of formula is called Clark formula. Okay? So here we have the local time of the Brownian motion. Of course, it depends on the Brownian motion, and it is square integrable since it is an L2 limit of something. Okay, so we can. It has a Clark formula, and here it is given explicitly. We have this x of t explicitly. It is here in this integral from r to 1, the derivative of s minus r, p s minus r, p of r minus 2, and so on. The first part here, this deterministic integral, is in fact the expectation of the local time. Maybe this is also a small fact that is good to know. The mean value of the local time at the point u is given by this integral. Okay. I recall that what this PR is Gaussian density given here. Okay. So, okay. Now we want to derive a similar formula, but for the local time of Gaussian integrators. Okay. So this is like a specific case, but the proof of it is a little bit different, or can be obtained without going in general framework. Okay. So now we go back to our integrator x, and we make this notation here, sigma of t as the norm of a and equal to 0 t. And maybe I made this remark before. This is exactly the variance of x of t. Okay, we suppose some condition here. A is invertible. This is necessary for the existence of the local time. A sufficient condition for the existence. And we need these two conditions here. Sigma square of t, this, the variance is non-decreasing, and it satisfies this integrability condition. Okay. In such case, the local time of the integrator, we denote it always rho of u, has also a Clark formula. Okay. But what is good here is that we integrate with respect to x itself. You remember when we defined the Gaussian integrator, it was defined, it was introduced, in fact, to integrate. That's why it is called integrator. Okay? And here we obtain
I have a question. Sorry.
Yes.
In this Formula 1, your variables are STR. What?
Yes, you're right. U and V are S and T.
Okay.
U and V are S and T. I changed it here. I forgot the denominator. what's good in this formula is that we integrate, it is similar to this one, but we integrate with respect to the integrator itself. Also, this first integral, you can check this is exactly the expectation of the local time. This first integral. Okay, maybe you can explain why these two conditions, 2 and 3, are given. Sigma square of t is non-decreasing. Since we have here sigma square of s minus sigma square of r. Of course, the function p epsilon that we always use, the function density, this epsilon should be a positive parameter. So this should be always positive, and that's why it is necessary to impose this non-decreasing aspect of sigma square. Now this third condition here, this finite integral, in fact it guarantees that what we integrate here with respect to x should be square integrable. Remember this remark, in stochastic analysis we integrate things that are square integrable, not like in real analysis we integrate functions which are integrable. And even in after the definition of Gaussian integrators, we define the integral of a function ht with respect to x, but when h is square integrable, okay? For h in f2, so we need square integrability to define integral. Okay, now if we take this integral here inside between parentheses, if we take its we want to check if it is square integrable or not, we will find we will need this condition. This condition is sufficient for it. Okay. We can compare the two formulas that we have. The first one for the Brownian motion and the second one for a general Gaussian integrator. And you can see how the second one is in fact as generalization. The first here, just PR of u, here P sigma square. Of course, we can denote this also R and R. In fact, this first formula is just an example of the second one. If we take the Gaussian integrator to be the Brownian motion, this formula is exactly the first one. Okay. But okay, before going to this next lemma, I go back to this condition 3 given by this finiteness of this integral. It seems to be a little bit complicated, so that we thought about a better condition that guarantees this one. Okay, we can find a better condition, more easier to check, that will imply this condition. Okay, so suppose that this function sigma square of t given by the square norm of a indicator 02 is differentiated with respect to t, okay, and such that its derivative is how to say, it is greater or equal than some function which is positive and increasing, and such that this function f satisfies this integral condition. Then this condition 1 is satisfied. Yes, we have 3 conditions here just to obtain this integral condition that we were discussing. But never mind, these 3 conditions are easier than the one we had before. So it is sufficient to compute this square norm of a indicator 0. We always have the operator. We can make this computation. check if it is differentiable with respect to t or not, compute the derivative, and try to find a lower bound function which is positive and equivalent, satisfying this import. And then for one single function, we can check if this condition is satisfied or not. Okay. Don't worry, we have some examples that where these conditions are satisfied. All the conditions that here are satisfied. So these three conditions just to obtain this one, okay? What I denoted by 1. And of course, we always need 1 and 2, invertibility of A and non-decreasing of the sigma square of E. So we can resume, we have like 5 conditions just to obtain this formula, right? Okay. Okay. Some examples. If we consider yesterday, Professor Xia Chen asked me for different examples. Here, some of them. So if we consider the operator of multiplication by a continuous function phi, such that it is bounded from below and above by two constant, non-negative constant, small m and capital M. So the operator is given by AH is phi multiplied by H. What is the corresponding integrator? It is good to ask this question, and it is good to answer. What we find is exactly the following integrator. This process, the integral from 0 to t of this function free from answer with respect to the Brownian integral. We recall that what is x in all the cases, it is the integral from 0, 1, a indicator 0 t. So we complete this function in S and we integrate it with respect to the Brownian integral. So this, okay? We have that just take h to be this integrator function and make this computation. What we find is exactly this integrator. And it happens that this operator has all the required conditions. Okay, we can check that. Okay, we have these properties. Okay, this one. Okay, the norm of A indicator 0 t square is differentiable. It is bounded from below by a function that satisfies this condition, and that we have also the invertibility. We have the invertibility of this operator, and we have the non-decreasing aspect of the variance. Okay. A second example, of course, here maybe I did not put all the details why these are two examples of how to check these conditions for this example, but I can leave it to you. It is not such difficult exercise. Second one is to take the identity plus the Volterra operator. This operator here, we can check that it has a norm strictly smaller than 1. And so this sum, identity plus V, is an invertible operator. Moreover, we can check also the other condition. Okay. Here, explicitly, the Gaussian integrator is given. We just have to compute A of the indicator 0 t, but A is simple. We have the identity plus this integral. I think we can compute. What we find is this expression for the Gaussian integrator. It is not maybe some usual process that we are familiar with. It is a little bit different. Okay, a third example also is given by an operator defined by following formula. A of h is given by h itself plus this integral operator on the right hand side. In fact, this operator is exactly this A is exactly the geometric series of the Volterra operator that I have just defined in example 2. Okay? So this third example can be deduced from the Volterra operator by this formula. Okay, and we know that if we have an operator with norm smaller than 1, then this series converges and defines an invertible operator. Okay. It is good, by the way, to ask the following question: how to find an invertible operator? We already have used some of these techniques, either by this way, or, for example, if you take an operator B with norm smaller than 1 and take identity plus B, then this one is also. So for these three examples of operator and for the corresponding integrators, we have an explicit Clark formula for the local term. So that's what is intended to okay. And now we move to self-intersection local time. I recall that we have proved the existence in the case of Gaussian integrators. So always we need this condition of invertibility of the operator, and we have seen that the local term of self-intersection can exist as a limit of L2 in L2 of the following. So it is obtained by means of this approximation. Okay. Okay. So we will try to obtain also a Clark formula for the self-intersection local. So a similar formula like this, but for this multiple self-intersection. So here we need some notation because the result will be a little bit complicated. So for a fixed t in the interval 0, 1, and for a fixed vector t1, tk, k, we define these increments. So we define this new process, but it contains increments. Now we are familiar with increments. Exactly, for example, in the first coordinate we have x t1 plus t, t2 minus t1 minus x t1. Of course, this value here is between t1 and t2. Okay, so it is like that we have t1, t2, t3, and so on. And we have a fixed t between 0 and 1. And with this t, we will take an element from each sub-interval, but with the same proportion. For example, we'll take this one, but the same proportion. That's all. So if it's tk minus 1, we'll take something like this. Okay? So this is t1 plus t times t2 minus 1. Okay? This is t2 plus t times t3 minus t2 and so on. And we are looking to the following increments. Okay? X of this minus x t1, x of this one minus x t2 and so on. And we do this for each t between 0 and 1. Of course, if we make t vary between 0 and 1, we will have all the possible increments. Just make this one with all the possibilities. So we take this general form of increments and we consider the following Gaussian matrix, which is a fact. This matrix is exactly the covariance matrix of this Gaussian vector reality. Okay. And what we do is we consider like the differences of the of two such Gaussian matrices. Okay. It seems to be a little bit complicated, but we will see after that it can be comparable to what we have obtained just before with the local time. Okay. Now that we have fixed this notation, the formula is here. So we suppose that A is invertible to guarantee the existence of the self-intersection local time. And we suppose that for each t between 0 and 1, the matrix is positive different. Okay. I'll go back to this matrix. What is R? What I denoted by this? It is the difference between B T1 minus B. It is the difference between two Gaussian matrices. It is the difference between two covariance matrices. Okay? But when we say this is positive, we impose this condition that this is positive definite matrix. Okay. Of course, these are symmetric matrices. The difference is, again, symmetric. We impose also that it is positive definite, which means that there is like a natural order in symmetric matrices. We can compare them between symmetric matrices. We say that A is positive for a symmetric, semi-definite matrix. We say that it is positive if it has positive eigenvalues. Okay? And so we say that this is positive if it has positive eigenvalues. In some sense, it means that this matrix is greater or equal than this one. There is like an increasing covariance matrix. Okay? So the condition is, we can write it in this way: BT1 is greater or equal than. This order is used between positive symmetric matrices. It is not okay. So, but this condition is to replace the condition, if you remember, of increasing the sigma square of t. The condition that we used to derive the Planck formula for the intertime parameter. Okay, under such condition, we denote by PR the density of the distribution, the normal distribution with covariance matrix RPT. Maybe I can recall this. We always use. If we have a Gaussian vector with a zero mean and covariance matrix, say gamma, which is invertible, okay? Or positive semi-definite imply invertibility, okay? Gamma invertible matrix. What is the density of this Gaussian distribution? I will denote it by P gamma. It is a distribution. This is supposed in RD, okay? What is the distribution? It will be given by 1 over pi to the power d over 2. And here we will have square root of the determinant of gamma and exponent minus inner product between x and gamma minus 1. Okay. This is a distribution of a Gaussian vector, okay, of a normal, the density of a normal distribution. Okay. But we are already using this from the beginning, since we have this function p epsilon. There are very one-dimensional examples of this one. Okay? Thus, this is the d-dimensional generalization. Now, under the invertibility and the increasing aspect of these covariance matrices, we have this formula, this Clark formula for the self-intersection over time. So we can write it expectation plus some stochastic integral. Okay. It's a little bit complicated, but this is the Clark formula. Okay. Here, just to compare the two results for the local time and the self-intersection over time, there, if you remember, we used that sigma square of t is non-decreasing to obtain this formula, Clark formula for the local time. What replaces this condition for the self-intersection over time is the increasingness of the covariance matrices. How to describe that the family of matrices is increasing? If they are symmetric, we can use the order between symmetric matrices. Okay. Some examples for which these complicated condition that is covariance matrices are satisfied. We can find really such examples. Again, we go back to this operator of multiplication, okay, by a function that is bounded from below and above by some positive constant. Again, this expression, we have seen it before. One have to say that one have to consider, to construct these matrices, there is some work that have to be done. One have to consider these increments and compute these Gramian matrices and check that these Gramian matrices are increasing. But in this case, it's not such difficult because these matrices will be diagonal matrices. Okay, so this example is an easy example. Okay. The next one is the identity plus the Volterra operator, and this is the corresponding integrator. It's not easy to check these properties when this k is 3 or 4 and so on, because we will have a little bit complicated matrices. But for k equal to 2, we can check the condition. Okay.
And the first example for any k, everything.
For any k, we can check. The matrices are diagonal. The comparison is very easy. Okay. But in the next one, the matrices become to be complicated, and the comparison is not so such easy. Or even I did not find another example where it is possible really to check this complicated condition. Okay. Next, I will move to another kind of representation. So this is the first representation, the Clark formula. So we have been able to write it explicitly for the local time and for the self-intersection local time for a large class of Gaussian processes. Now I will try to present another kind of representation. It is given by a series representation. Okay? So we'll try to write the local time or the self-intersection local time as a series. There is a specific series, okay? Of something that I will define. Okay? Different representation for the same thing are important. Integral representation, series representation, each one can be useful in some situation. Okay? It's like maybe you have some specific function, for example, in real languages, and they have different representation. They can be represented by an integral, they can be represented by a series. Okay. This series that I will consider is called the chaotic expansion. Okay, the chaotic expansion. Okay, so we have Clark formula and here chaotic expansion. What I mean by I will redefine and try to explain it. So we need first of all some properties of Hermite polynomial because they will appear a lot in this kind of representation. So I recall the definition of Hermite polynomial. They are obtained as derivatives of this exponent of minus x squared divided by 2. Okay? Of course, we derive n times and then we multiply by exponent x squared by 2 divided by 2, and what remains is a polynomial. And we multiply by minus 1 to the power n, so that it is a monic polynomial, okay? And the dominant coefficient is always 1. The first examples are here given explicitly. Okay? Of course, the important properties of this polynomial are given just in this following slide here. So this sequence is an orthogonal basis of the following Hilbert space. What is this Hilbert space? It is L2R exponent minus x squared divided by 2 dx. What does this mean? This is the space of all measurable functions from R to R, which are square integrable, but with respect to this measure, exponent minus x squared divided by 2 dx. Okay. So it is called L2 since there are square integrability, but with respect not to the big measure, but with this Gaussian measure. Okay. This family sequence of polynomials is an orthogonal basis, so that each, of course, the inner product is given by this expression. And this is Hilbert space, and now each function here that belongs to this space can be expanded with respect to this empty polynomial. Right? Means that if H belongs to this space, then we can write it as a series of some coefficient multiplied by empty polynomial. Okay? This series converges in L2, and these Hn are orthogonal in this space. Okay? It's like you have an orthonormal or orthogonal basis in Rd, but here it is an infinite dimensional space, but you still have an orthogonal basis, so you can develop any vector with respect to the space. It is important from a geometric point of view to use orthogonal basis in Hilbert spaces. They can be useful to express vectors to make a lot of calculation. Okay. Here, the norm of Hn in this space means that if we take Hn star itself, we will find n factorial. This is the norm exactly, by the way. Just we need to divide it by square root of 2 pi. Okay, this is the norm. This function here is the generating function of the element polynomial. What does it mean? It is such a function that it has this series expansion, but the coefficient, if you look, you develop this function with respect to t, and what you find as coefficient are element polynomial. So that you have to understand it as, if we want to get element polynomial, of course we have the definition, but we have another way. This is the generator function. We take this function, exponent tx minus t squared divided by 2. We try to make Taylor series for it with respect to t, and the coefficients that are obtained are element polynomial. Okay. Now this is in like this sequence of element polynomial is an orthonormal basis in this one this space constructed over R, but we can do the same thing in RG. So if we take the same definition here, but just we change R by RD and here x squared by the norm of x squared, what we find as an orthonormal basis for this Hilbert space is this product of element polynomials. Okay, so this sequence, this family here, okay, Hn1 from x1 times and so on, all these polynomial form an orthogonal basis of the Hilbert space given by this function. Okay. Now, why we want element polynomial while we are doing some stochastic analysis? Here is how they appear in the first form. So if we consider the standard Gaussian random variable, eta, and we consider this L2 omega sigma of eta p. What does it mean? It contains all the random variables which of the form that are measurable with respect to eta. So measurable with respect to eta means that it is a function from eta. And these random variables should be square integrable. And so what is the form of the elements of this space? It is, they all are of the form of function from eta, where f, where this function should be in L2 of R, in this Hilbert space that I have defined before. Okay. So now we have like an isometry between two of the Hilbert spaces, the following Hilbert spaces, L2 of R with this Gaussian density, and L2 of omega, and this Hilbert space of all square integrable random variables which only depend on eta. Now we have two isometric Hilbert spaces. We know we have an orthonormal basis for this one, so we can deduce an orthonormal basis for this one, the second one. And from that orthonormal basis, the expansion of any element here, that will be called a chaotic expansion. Mainly, if we consider alpha in this space, then it will have this this series expansion, okay, for some coefficient an that can be obtained by the inner product between alpha and Hn of eta, okay, and here element polynomial from it. This is chaotic expansion for this random variable. Okay. So we have in this space we have an orthogonal basis obtained by Hn of eta for n from 0 to infinity. And each element here, each random variable in this space can be expanded in this way. The good in this series is that it converges in L2 sense, and all these terms in this series are orthogonal in L2. means that if we make expectation of hn of eta and hm of eta for different n and n, we will find zero. Okay. It is like an orthogonal basis in a Euclidean space. So, okay. Now we do the same, but instead of taking one single random variable, we'll take a Gaussian vector, and then we'll even take the things to another level and consider the whole Brownian motion. Okay. Just before going further, so there is an example of chaotic decomposition. If we consider an element from L2 of 0, 1, and we define the following, what we call stochastic exponent. I have chosen this example because it is very useful in other results. So it is the exponent of this integral here of h with respect to the Brownian motion minus 1/2 the square norm of h. First, if we look to this, this is a random variable, of course, and we can check it is square integrable, and we can find a chaotic expansion for it. But first, remark that this random variable here given by this integral, it has a variance given by the norm of h. Okay. This is exactly the variance is the square norm of h of the variance of this random variable, and so if we make this quotient, we will find the standard quotient random variable is eta, and it is clear that this random variable only depends on this theta. This is a constant here. So we have a random variable that depends on the standard Gaussian random variable eta, so we can derive its Euclidean expansion, chaotic expansion. But it is easy for this example because here we can use the generating function of element polynomial. Just look at this expression here, and I will go back a little bit and compare with this, the exponent of dx minus t squared over 2. Okay? So if we apply this formula really deep, we exactly will obtain this expansion. Okay? So we can easily obtain the chaotic expansion of this random vector. Okay. Now let's take another level. If we consider a standard Gaussian random vector, so we have eta 1, eta d, all of them standard Gaussian random variables, independent, okay, when we take the whole vector. Now we will consider all the random variables which only depend on this vector, so they are function from eta 1, eta 2, eta d, and they are square integrable. I denote this space by L2 omega sigma of eta. Square integrable that depend only on theta. We can, if you have a random variable that only depend on a finite number of other random variables, then it is a function of those random variables. This is good to know. So each alpha here will be will has the form of a function from eta 1, eta 2. Okay. Now, how to derive its chaotic expansion? We deduce from this that we have an isometry between these two invert spaces. Okay. L2 from Rd with this measure here, and L2 omega sigma of it. Okay. I have presented just before the orthogonal basis for this space, which is obtained by products of our polynomial. So we use this orthogonal basis and to derive an orthogonal basis, this new invert space. Okay. So what we deduce is that each alpha in this space here has the following representation. Okay? It's a series from n equal to 0 to infinity. And here we will have some coefficient multiplied by hn1, eta1, hnd, eta. Of course, it is a little bit more complicated, but it is comparable to what we found in the previous situation. Okay. Now we will go further, and instead of taking a Gaussian vector, we will consider the whole Wiener process. Okay. So we consider the Brownian motion and the generated sigma field. So the sigma field generated by all the Vt or t between 0 and 1. So what is the chaotic expansion of a random variable? It has the following form, of course. The expectation of alpha. This is the first term plus the sum from 1 to infinity In. Now, what is In of Fn? It is a multiple stochastic integral. Okay. Fn will be some symmetric square integrable function on 0 1 to the power n. And here, so it is function of n variables, and we integrate it with respect to bt1, bt2, and so on. Of course, this is a complicated integral. This is a stochastic integral, an E2 stochastic integral. But at least how one can understand this, we integrate this function here, fn t1 tn, with respect to t1 to bt1. So we find a new function that only depends on t2 tn. We integrate it with respect to bt2 and so on. Okay, it is a multiple stochastic integral. Okay. Maybe we will not use it too much. Okay, so at least one, okay, has an idea. This is a multiple stochastic integral. Okay. In addition, of course, this is a chaotic expansion. We can derive from it the square norm of alpha. Okay, it will be given by, since we have orthogonality of all these summons here, then we can obtain the following expression for the L2 norm. Okay. A good question here is, why in the previous two examples we had Hermite polynomials in the chaotic expansion, and suddenly here we had multiple E2 integrals? Why the natural generalization of Hermite polynomial is given by multiple stochastic integrals? The answer is given by this formula. A specific case of multiple integrals can be described by Hermite polynomial. If we take a function ft1 tn as the same function h of t1 multiplied by h of t2 and so on, this multiple integral can be expressed by Hermite polynomial. You see here h. So this magic formula explains how from chaotic expansion containing Hermite polynomials we move to chaotic expansion containing multiple integrals. Okay. It's like that the Hermite polynomial are specific cases of multiple stochastic integrals. Okay, I tried to explain what is chaotic expansion just to understand what it is, because I will present the chaotic expansion for the local time or the hour Gaussian integral. Okay. So here is the result. Assume that our operator A is less or equal than 1. This less or equal than 1. I think I I made a mistake. Assume that it is invertible. Okay, not less than rather one. Okay, I will correct this before giving you this file. Okay, so assume that the A is invertible to guarantee the existence of the local time for the Gaussian integrator. Then the E2 expansion. By the way, we say E2 expansion. Yes, or chaotic decomposition, or chaotic expansion, or chaos expansion. This is the same thing. Okay. So we have explicitly what is this chaos expansion of the local time of the Gaussian integrator. Right. So it is given by this series. We have here an integral with respect to t, and we have n polynomial u divided by sigma of t. This is deterministic. P sigma t square of u. Again, we have these Gaussian densities up here, and we have n polynomial. This is the only random one that appears. Okay, so n polynomial xt itself divided by sigma t. Okay. I also have, okay, prepared a short proof for this result. Not the full proof, but at least one can understand how we obtain this and why this is exactly the E2 expression. Okay? So, the local time is given by the L2 limit of this approximation. And so the idea is to write the chaotic expansion for this random variable, P epsilon of xt minus u. And then integrate it and make it. Okay, we'll do this here heuristically, not rigorously, but at least you understand how we derive. Of course, in our article it is rigorously proved, but here just to explain the idea, how this expression appeared. Okay. So, if we use the standard Gaussian random variable eta xt divided by sigma t, we record that the integrator is a Gaussian process and it is has zero mean. So if we divide xt by sigma t is the square root of the variance, we of course we will obtain standard Gaussian random variable. Now. This is a standard Gaussian random variable, so p epsilon of xt minus u is a function from this eta. It is given exactly here. Okay? P epsilon sigma t eta minus u, so it is a function from eta. And we know how to obtain the chaotic expansion for a random variable that only depends on one single Gaussian standard random. Sorry.
This is the chalk.
Ah. Okay. Yes, but now how from this expression we move to this series, okay? You remember how to obtain this here. When alpha I presented in some slides, when alpha belongs to L2 of omega sigma of one single random variable, not a vector, one single random Gaussian, standard Gaussian random variable, then the chaotic expansion is given by a series an hn of it. Okay? And how to explicitly obtain what is an? Because this is like orthogonal basis. How to obtain the coefficient is the inner product between alpha. Okay, this is exactly expectation of alpha multiplied by Hn. So this is the coefficient are obtained by inner product between the vector and the elements of from the orthogonal basis. Okay. Now we just need to compute this and show that it is equal to this formula here, this huge formula. Okay. So this is Hn of it. Okay. This is the factorial. We just need to obtain this. Okay. We can do some calculation that can be really seem to be very long, but they are accessible. For example, in the first, I will leave for you for of course the document, and you can check it carefully. But I will explain the main idea here. Okay? So, making this inner product, okay, between alpha. Alpha is our P. Alpha is in this case is P epsilon xt minus u. Okay, and which can be written, xt can be written sigma t times t, okay? Like an and of course Hn of it. So if we make both of them are function from eta, if we make the expectation, what we obtain this first integral here, okay? P epsilon sigma t v minus u, Hn of v, P1 of v, okay? We have expectation of product of two random variables which only depend on eta, which is a standard notion. Okay, so we obtain this first integral. Then we use what is the definition of Hn. You remember, it is obtained from derivatives of P1, exactly, exponent minus x squared divided by 2. So if we write this formula, we can replace Hn P1 by the nth derivative of P1, and we need this minus 1 to the power. But then we can make an integration by parts a several number of times, n times, and we will transform this derivative here to the other function. Okay? Okay. Now that we have obtained the derivative here for the first function, what we will do is that it is a derivative with respect to the variable v, but we can check that it has a relation with the derivative with respect to the variable u. You can check the formula. Sometimes I really insist to show these details because they are really accessible to undergraduate students. They can understand this. Because this is just integration by parts. It seems to be wrong, but I know they can understand this. Okay. So, for example, here, why the derivative with respect to v of this, you can check it. P epsilon, let's say sigma v minus u. Okay. If you derive with respect to v, you will find that this is exactly minus, this is minus sigma, the derivative with respect to u of the same function. Okay? Just derive it with respect to v, try to derive it with respect to u, and see the difference. You will find easily this formula. Okay? So if we repeat this n times, of course, we will find this new formula here. And now we transform the derivative with respect to v to a derivative with respect to u. But u is not the variable of integration. So we can get this derivative outside. Okay? And if we derive outside, what remains here, how to compute this integral of this product of two these Gaussian densities? Of course, we use convolution. We have these convolution properties of this family of functions. Okay. Yeah. So the result will be this one here, and its nth derivative. Of course, again, the derivative of these Gaussian densities will lead to the appearance of n. Okay. Of course, now we have obtained this coefficient. Okay, we have obtained this coefficient, so we have obtained this chaotic expansion for just p epsilon xt minus u. Now, just if we make some formal calculation, if you let epsilon tend to 0, this epsilon will disappear here and here and all the pieces, and this one will be this to the power n will be 1. Okay, this hn will be hn from u divided by sigma t. This epsilon will disappear, and just adding this integral, we exactly find this. Okay. Sometimes you don't need to go. I mean, you don't have the time to go through the proof, but at least you can understand the result. Okay. Anyway, now I will switch to something else.
There will be a break.
What do you think?
How long is the second part?
10 pages, 10 slides. Not too much. I don't know. It's up to you.
Let us continue.
Okay. I will talk about polymers, why polymers are related to self-intersection and self-intersection. Okay. First of all, a polymer is a long chain consisting of atoms or molecules called monomers. Okay. So a long chain, a long molecule, and it is constructed from small pieces of the same piece of atom, the same atom that is repeated, or the same small molecule that is repeated many times. Okay? Here is some photos, just after. Finished? Okay. Okay? For example, our DNA, it is constructed by the same piece that is repeated many, many times. Okay? Of course, I don't remember how exactly it is. This is a small piece I call it, but it is this. Yes, there is a small piece that is repeated many, many times, and the molecule that you obtained at the end is very, very long, very huge molecule. Okay, this is an example of polymer. Okay, it is a natural polymer. It exists in nature. Okay. Also, before moving even to synthetic polymers produced by human beings, I can also name proteins. They are very long molecules that are obtained by the same small molecule that is repeated too many times. And maybe I should say that these molecules are very huge. For example, you can find in the same molecule a number of tens of thousands of these small monomers. So they are very, very long molecules. Okay? Not the molecule that we have learned in chemistry. They are very, very small. Okay? But these ones are very long, and there are other examples that are produced by human beings, synthetic polymer. They are mainly, we can find them in plastic devices. Okay, there are a lot. There is a big industry using polymer. Okay. Okay. The question: what could be a mathematical model for polymers? So if yes. If we want to study polymers, what to use from a mathematical point of view, okay? Because they are very long molecules, so they are they have some specific shape, and depending on the media, surrounding media they are living in, they have many properties, okay? So how to study them? But as you see here, this is a microscopic picture of polymers, and it shows that their shape is more or less like the Brownian trajectories. Of course, the mathematician will look from, according to his knowledge, will say this is, we can substitute these by trajectories of the Brownian. Okay. And it happened that basic mathematical model used to study these polymers are of two types. There is a Joyce model where the random walk is used. You know that random walk, it is like a very simple movement in the plane or in RD, okay, so you just need to go a step in, you have, for example, in the plane you have only 4 possible directions, okay, so either you move to the left, to the right, above or up, or, okay, up or down, okay, and with if it is, let's say, with the same probability, okay, so you will have a movement like this, for example, and so on, okay, and these, by the way, these random walk are very related to the Brownian motion. I can say formally, maybe this is the primitive of the Brownian motion. The Brownian motion is like a limit of such kind of random walk. Okay. Now this can be used as the first model for the polymers. Okay. And another one, more developed model, uses the Brownian motion. If you go back to maybe the first lecture, maybe, or I think the first lecture, you will find some 2 photos, some simulation of the Brownian motion. If you check the planar Brownian motion, you will see that it's not so different from these kind of pictures. Okay. Now there is a problem when using the Brownian motion as a, or random walk as a mathematical model for polymers. The problem is that, as we said yesterday, I think, the Brownian motion has self-intersection, has multiple points. It always intersects itself, and we have dependence with respect to the dimension. Okay? But of course, if you have a real shape, a real molecule, it cannot intersect itself. Imagine that you have this is like a polymer, so it is there are some monomers that are connected. Okay, it cannot go through itself again, because these are like balls. Okay, molecules as like balls. You cannot 2 balls cannot intersect themselves. Okay, because they are full. They are not just mathematical. Okay, so they cannot intersect themselves, and this is called the excluded volume effect. Okay. What does this mean? If you have 2 balls, there is always a minimal distance between their centers. Take any other ball. Okay. What is the minimal distance that can be obtained between? Yes, exactly. This is the radius 1 plus the radius 2. You cannot have the situation. They are 2 balls. Okay. So there is like an excluded volume. There is a situation which is excluded. You cannot have overlapping. So this is the problem. In nature, we cannot have this kind of intersection. in mathematical model, Brownian motion or random walk, we have intersection. We have a lot of intersection. So there is like a problem in this model, and how to solve it. How to solve it needs, first of all, to well study this self-intersection local time. Okay. For those who make chemistry and study polymers, of course, they at least found a solution how to reduce the effect of this self-intersection in their mathematical model. So how they do this exactly? Every path of the Brownian motion receives a penalty. It receives a penalty. This penalty is expressed by this function exponent of minus beta ht. So beta is some constant, and ht is given by this formal integral. But this is exactly, of course, these are not the notation that I used in my lecture, but this is exactly the self-intersection local. Okay? This integral describes how much time, when we write delta 0 bu minus bv, it means we count the u and v such that bu is equal to v. So we count the time when we are in the points of double points, bu and v. Okay? So this ht, this is the self-intersection local time. And while we multiply by this exponent of minus beta ht, why this is a solution, why this is called the penalty? It means that if you have a lot of intersection, it means that this ht is very big. It has a big value. Like we have seen, it tends to plus infinity in three-dimensional cases. But if you have a very big value and you make exponent of minus beta, this value, and with beta is strictly positive, of course you will have very small thing. Exponent minus beta times ht. Okay? This is very big. It is close to plus infinity. Let's say plus 1 million. And if you make exponent minus, you will find a very small thing. Right? So this is a way to reduce it. How do they use this? For example, if they make some computation energetic, for example, computation or something like this, if they have some integral to compute, they will always put this factor in their computation. Okay?
So a kind of renormalization.
Yes. It reduces the effect of a self-intersection. It reduces the effect of these multiple points which they do not like. Okay.
And also looks like Boltzmann
Yes.
factor.
Yes. Yes. It seems to. Okay. Okay. I want also to speak about something else also related to polymers and self-intersection local times, which is the end-to-end distance in polymer models. So let's say that this picture is a very simple picture of a polymer. Okay, so that these black dots are represent some monomers, and these here vertices just like chemical bonds between them. Okay, so in black this is a polymer. Okay, and this sign in red here, just this is the end-to-end distance, the distance between the first monomer and the last monomer. Okay, this is important aspect, and we will see why it is important. This end-to-end distance. It is like that you have a chain and you look to the end-to-end distance. It's important from a chemical and physical point of view. Okay, and next we will see why is it important. For example, in the fluoride theory, fluoride is scientist. So in his model, he tried to compute the total energy of a polymer chain. Okay? Try to compute the energy of this polymer. Okay. So he decomposed this energy. He denoted it by F. And he decomposed it into two parts. This first part here corresponded to the energy of obtained from the entropy. Okay, the freedom that the polymer has, because it has possibility of movement. There's the possibility of changing its shape. So this is the first part of this energy, and the second part is related to the interaction between the different monomers. Okay. So here these parameters, T is the temperature, this constant B is the monomer size with the diameter or the radius. This small v is a constant that characterizes the local interaction between two connected monomers. The small r is the end-to-end distance that I was speaking about. And this capital N is the number of monomers. So that you have a big chain, you look to the r is the end-to-end distance, capital N is the number of monomers, and so on. You can see here that this first part of the energy is proportional to the end-to-end distance. If the end-to-end distance is long, it means that the chain has more freedom to move, and it has more entropy, it has more freedom. Okay. The second part is inversely proportional to the end-to-end distance. Because the second part, it describes the energy of interaction between different monomers. So if the end-to-end distance is very long, the monomers have less chance to interact. They are away each one from the other. So this energy will be small. Okay. Now what he looks for from this description of the energy is he looks for the end-to-end distance that minimizes the total free energy. What is the end-to-end distance that realizes like equilibrium? Okay. So at equilibrium, the energy is mean. Okay. Now we have the expression of the energy. How you look for the value of R that gives you the minimum value. Answer. You make, first of all, you make a derivative with respect to R. Okay? If you want to look when it is minimal, you make the derivative of F with respect to R and see when it is 0. Check, find this value R for which we have this. This corresponds to the equilibrium, to the minimum energy. Okay? It is not too hard to derive with respect to R, I think, and to find, to solve this equation. This is a simple task, and what is the solution? It will be some constant times n to the power nu here. Okay? So you can compute and solve this equation, and you will find some constant times this n, the number of monomers to some power. This power here is called the Flory exponent, and it can be explicitly obtained. Okay. So you see how the end-to-end distance is important in studying polymers. Okay. It has a relation with minimum energy, with equilibrium, and so on. So, from a mathematical point of view, how to do some theory in this context of end-to-end distance. In fact, the self-intersection local time is the appropriate tool to replace the intramolecular energetic interaction between molecules. This means the energy of interaction between different monomers. How to replace it or how to describe it from a mathematical point of view? We use the self-intersection local time because it describes the situation in points of self-intersection when the points are very close. Okay? This can be a substitute to this energy of interaction. And for example, like exactly what we were discussing in this Flory theory, what is the end-to-end distance, or what is the link between end-to-end distance and energy of interaction. Here, how to substitute this by means of Brownian motion and self-intersection local time. So, how does the self-intersection local time depend on the end-to-end distance? Okay. So, the polymer can be, we can imagine the polymer as some trajectory of the Brownian motion. And we look, this is the end-to-end distance. The Brownian motion starts always from 0. So the end-to-end distance is simply the last value, which is b of 1. This is b of 0. This is always the origin. This is the end-to-end distance. Okay. What is the effect of this value on the points of self-intersection, on the self-intersection local time? Okay, at least I will present two results in this direction that were proposed to answer this question. Okay. In one-dimensional case, so if we consider a one-dimensional Brownian motion and we define its self-intersection local time, we have seen this definition, the double self-intersection local time. Then it was proved by the following authors that for any alpha strictly greater than 1 and beta equals 1, we have the following asymptotics. Okay? So when a tends to plus infinity, okay, so a here is a real number. When a tends to plus infinity, we have here the conditional expectation of this self-intersection local time to the power alpha with respect to the value of b of 1. So b of 1 equal to a, and then we will let a tend to plus infinity. As I said, the value of b of 1, this is exactly the end-to-end distance. So if we want the end-to-end distance to see what happens when it becomes very large, we will take a to plus infinity and we will see how the self-intersection of the time will behave. Okay? So, and the behavior is given by, it is a big O of the norm of a to minus beta. It means
for any alpha and any beta.
for any, yes, beta is 0, 1. Any
Yes, but they are not related to each other? Just
independent value, yes. Yes. Of course, it seems to be very rich for any alpha or any beta, but maybe a simple remark is that, of course, this, when a tends to plus infinity, norm of a to the power minus beta tends to 0. So it means that this self-intersection local time will be very small when the end-to-end distance goes to plus infinity. When the end-to-end distance is very long, there are very small number of self-intersections. Imagine that you have a chain that is very long, it has less chance to make self-intersection. In the same.
For the motion, it is the case where we have like a continuous curve defined on a compact, but it has infinite length, so you can
yes.
one piece.
Yes, you can take the
if you have enough of
yes.
these polymers.
Yes, yes, of course. Okay. And the same authors try to look at the situation in two-dimensional case. Okay? So in two-dimensional case, maybe it will be more, one can imagine better. But in two-dimensional case, the situation is a little bit more complicated. We even have seen the multiple points in two-dimensional Brownian motion. If you remember, the two-dimensional Brownian motion has points of self-intersection of any multiplicity. Even, maybe I did not tell this, you can find points of infinite multiplicity.
You can mean notation rho 2 of A and alpha?
Yes, this is a new, like a new definition of the local time, but instead of integrating over delta 2, we integrate over this new distance to A alpha that I will draw later on. Okay. So the situation is very complicated, and this will appear even in this result. First of all, what is this delta? So delta 2A, if you remember, delta 2, this is a set of S T, which S less than T, both of them between 0 and 1. So this is this triangle here. Okay. This is for S, this is for T, or T1, T2, okay? This is 1 and 1, okay? We used to use this delta, okay? But now they will change it to delta 2 A alpha, given by the definition here. So we have T1 and T1 is less than T2 minus something. Yeah, or then rho of A higher power minus alpha.
Yeah, so the definition is there, so we can follow.
Okay. And this is less than.
So which definition is wrong? This one on the slide? Yes, I think the first is T2 less, okay? Yeah. Because both of them should be between 0 and 1. And T1 is less than T2 minus something, okay? So the second inequality there, here, this is okay, but just here, this is T2, okay? This is T2, this one. Okay. But then there is no estimate for T1 that it is bigger than 0.
No, it's okay, both of them are true. What? Yeah. But both of them are true, okay? Both of them are true, okay? There's no. This
I don't
is.
see why T1 should be.
It cannot.
Non-negative. It is not given if you say that the first minute bullet.
No, it's true. Both of them are true.
Oh, okay.
Yeah. Both of, and this is what is meant. Okay? So this one. So instead of taking the full this integral,
So we'll take like this. Only this one. So we'll take T1. Yeah. Yes. That's it. You see? So we are the way from the diagonal, because this diagonal makes all the problems. Okay. So this value here, you can check that this is the norm of a to the power minus 3. Okay. And this one too. Okay. This is norm of a to the power minus 9. So of course, if you take then a to norm of a to plus infinity, this will tend to 0. So this triangle will be very close to this one. Okay. Okay. So if we work on this new feature here, and we define rho to A alpha to be the L2 limit of the approximation corresponding to T1, T2 in this set. Then, if you make conditional expectation of the local time, self-intersection local time, with respect to the value of B of 1, which is again, this is the end-to-end distance. So how the self-intersection local time behaves with respect to the end-to-end distance. And we have three different options, three different possibilities. Either we find a finite limit if this alpha here, this like alpha is like the speed, some speed, how to converge to the real self-intersection local time. So if alpha is equal to 2, then we find some this constant. If alpha is smaller than 2, we find some 0. Alpha is greater, stricter than 2, we find plus infinity. Okay. So this is a description how the end-to-end distance has influence on the self-intersection local time, and in the planar case we have like a lot of surprises. Everything seems to be possible. We can have the limit can be 0, which means that if the end-to-end distance is very long, then the self-intersection local time will tend to 0. This is quite one can imagine it, but it may also go to plus infinity, which means even if you take this extremity, it was somewhere here, so this is like a Brownian motion. If you take this extremity to very way, still you have a lot of self-intersection, because the situation in the planar case is very complicated. Okay, but also you can take this this end-to-end distance to plus infinity in such a speed that the self-intersection local time will be very like will go to some finite limit, right? Okay.
So, but in the one-dimensional case, you also consider only alpha bigger than 1. So probably for alpha equal to 1 and for alpha less than 1, there will be also some other behavior. So somehow corresponds to alpha bigger than 2 in the planar case.
But here,
no, it's different, it's opposite, yeah? Yeah, for all big alphas we have converges to 0, and
yes.
in the planar case vice versa.
Yes, but here, for example, we do not change this delta 2.
Yes.
We take the self-intersection local time that we defined before. Okay, so we do not change its definition, and we have this result. It is.
But still, what's going on?
Yeah. Yes, it's good to ask, of course, to understand what happens if alpha is less
than 1.
Yes, equal to 1 or less or equal. Okay. Yes, of course.
In the planar case, you consider the first power of intersection, self-intersection.
Yes, just to the power 1. Just to the power 1. Yes, they are not so
So
similar.
they are different alphas.
Different alphas.
Different notation, different meaning of alpha.
Yes, yes. Okay. Of course, there are a lot of questions not without answers.
Yes, this is science.
Yes, of course. Maybe the new generation will solve. Okay. Thank you very much.
The sound for questions
Or answers.
or answers for the last problem or the problem before. Okay. No? Okay, if no, then we end for today, and tomorrow we will have the same schedules, so we have longer lectures, but on Friday you are free, and we too. If you will have some questions, please come and we can discuss.
Tomorrow, not on Friday.
It's tomorrow. Okay. Okay, then see you tomorrow as usual.